Polymer exam, and we're going to deal with a lot of dynamic mechanical testing analysis. So when we do dynamic mechanical testing, remember G prime is your storage modulus, G double prime, again, same thing, E prime, E double prime. These are your storage. These are your loss moduli. So the loss modulus, we know that these are going to correspond to your in plane, or in phase, excuse me. This is going to be out of phase. We also know that this is going to be your elastic contribution. This is going to be your viscous. And we know that these should, this contribution should dominate at when temperature is very, very low, when our strain rate is very, very high, when our frequency is very, very, very high, and when our time is also very, very, very short. So time, temperature, strain, frequency equivalents. It's going to be the opposite here. So viscous when temperature is very, very high. So you might be asked to kind of draw an equation where frequency accesses switch with some of these values. When your strain rate is very, very, very low, we saw with the silly putty, our frequency is very, very low, when our time is very, very long. So that's kind of the key aspect of solving some of these problems. So studying three mystery materials, they need a polymer expert to give insight what they created. We're looking the structure of the polymers and the mechanical response. We don't have FTIR, we can run dynamic mechanical testing. So we have three polymers. So the first question, we could kind of see some of the response. So first question is asking us which symbol corresponds to G prime and G double prime respectively. So obviously our storage or loss moduli. Well, just from this discussion we had previously, we know that the in phase, or our G prime or our E prime, should correlate when our temperature is very, very low, our strain rate is very, very high, or our frequency is very, very high. We need to see which, at high frequencies, which is dominating. Let's take a look at just the blue, for example. So which symbol is dominating, the circle or the triangle? Well, we know at high frequencies, the circle is dominating here. So that's going to be our G prime, and our G double prime should dominate at very, very, very low frequencies, low strain rates. So that is the triangle. And that's just from the discussion we basically discussed before. Now we're asked to figure out what's the calculation, or excuse me, calculate the relaxation time of each polymer. For what frequencies will the polymer behave like a liquid or solid? So we know that that crossover point is where we get our relaxation time. So I can see for my red here, this corresponds to a frequency. Let's call that, let's call it 3. So I know that my relaxation time, tau, is going to be 1 over the frequency. So it's going to be 1/3 seconds. Now let's go do my color for green. Let's say this is, let's say it's like 0. Excuse me, I didn't change my color. So right here, I'm going to call my green frequency. It's going to be, I'm going to call it 0.8. So I know that my relaxation time is going to be 1 over 0.8, whatever that value is. And then for blue, I'm going to also have this. I'm going to call that 0.5. So frequency equals 0.5. Relaxation time is equal to 1 over 0.5. Excellent. So that's the relaxation times for each polymer. What frequencies will each polymer behave like a liquid or solid or liquid? So we know that for, let's do for blue, for example, here, we're going to be liquid or viscous. And for high frequencies, we're going to be elastic. And the same will occur. Basically, if it's greater than your this kind of relaxation frequency, it's going to behave like a solid. If it is less, it'll behave like a fluid or liquid. Excellent. And finally, rank the TG of each polymer respectively. What can you deduce about the structure of the polymer? Well, we know from our discussion previously that our TG should scale directly with relaxation time. So we see that our TG, this TG is greater than my green TG, and my timer's going off. Echo, stop timer. Remote teaching never is boring, never boring moment, which is greater than the TG here. So the lower the relaxation time, the lower the TG. So our blue has basically the largest relaxation time, so that will give us our largest glass transition temperature. So remember, that relaxation time is like how quickly it could respond and to a perturbation. So if the relaxation time is longer, we also know that polymer is going to be more bulky. There could be some interactions. There could be less free volume, et cetera, et cetera, et cetera, that we kind of know from our discussions of, you're all TG experts, as you showed in the second exam. So you could kind of write and talk about that in terms of what the structure. So there might be, for this polymer, there could be these kind of bulky groups. There could be a lot of these double bonds. There could be these HC double bonds to O, intermolecular interactions. Lots of things can be going on, but this is the kind of the key relationship that we're looking at here. So the TG of the blue is greater than green than the red TG. All right, excellent. So it turns out polymer wasn't a new material, but instead it was just our old friend gamma MA. And we see these distinct peaks when we're looking at the log of our loss tangent versus temperature. So this is our polymer right here. So label each peak and describe what can be going on with the polymer motion going here. PMMA is amorphous. So this is important because we know we need to label these alpha, beta, gamma, delta. We always start from high temperatures and decrease in terms of our labeling of the peaks. That's standard protocol here. Now, the question that we have to ask ourselves is, PMMA is an amorphous polymer. So we know that the largest glass transition, or actually the largest temperature, excuse me, I gave it away, at the largest transition at the highest temperature, that should either correspond to a TG or TM. But here, we know that we don't have a TM, so we're only going to have a TG. Now, a semicrystalline polymer might have another peak. We'll definitely have another peak later on, corresponding to melting, but let's not get into that for this polymer. So now the question is, what type of polymeric motion or transition could be occurring here? We know this is TG. Now, as you go down, the magnitudes of these peaks don't really matter too much, but we know this is our next highest temperature peak. So perhaps beta, we're looking at kind of cooperative motion. So let's say at beta, if we draw our polymer as kind of this connected series of monomers, we know that the glass transition is when we have like 30 to 100 monomer movements moving collectively. But perhaps at beta, 1, 2, 3, 4, 5 of these groups are moving collectively. So our monomer groups here are wiggling and moving, and they're kind of collectively like moving throughout your material. So that can, collective motion is very difficult. You need high temperatures to do that. Now, the gamma peak, lower temperature, right? So maybe now these monomer units aren't moving collectively, but perhaps this long bulky side chain is rotating around that carbon backbone. Again, very difficult to do, right? It needs a lot of thermal energy in order to rotate that, but we're still at relatively high temperatures. So that could be that rotation going on here. And then the last peak, the lowest temperature, the lowest thermal energy, maybe this peak is, maybe this, this side chain is just wiggling. So that could just be a wiggle. So not rotating around that backbone like we saw here. Why can't we switch these two? Because we know that there's not enough thermal energy at this lower temperature in order to kind of rotate that entire side group around that backbone bond. So we need higher thermal energy to do that. So you can't kind of mix the two up. You don't need to know exactly what type of motions, but when you're proposing what could possibly be occurring, you can't kind of switch and say, my TG is here, or, there's not enough thermal energy to do that. So as you're working through these problems, just kind of propose some ideas and make sure it makes sense in terms of the thermal energy that's available for these problems. Excellent. So that's it. You're done with practice exam 1. So congratulations, and practice exam 2 is coming up very, very soon. So I'll see you all in the next video. We'll work through 4 more problems, and then you'll ace exam 3. All right, and you'll be done with MEC 202. All right, excellent. Thanks, and I'll see you in the next video. Bye.